what we're going to do, and one of the nice things about, sorry, jumping back in kind of blatantly, one of the things that's great about VSEPR theory is you can use it to apply to larger molecules. And just by larger molecules, I mean things that have more than one central atom, uh, because it works the same way no matter what we're talking about. Okay, so I just want to work a couple of examples. We're not going to do a lot of thinking about huge things, but I just want to point this out. This is going to be very important when we get into organic and start doing those kind of things as well. All right, so let's look at ethylene. Ethylene C2H4. Um, and if we draw ourselves a good Lewis structure for this, right, always start with a good Lewis structure, we'll realize, right, the two carbons have to be connected, right? Then we're going to put hydrogens evenly. Okay, and we'll need a double bond in the middle to make sure all of our things are good. All right, so this is what we're doing. Notice we got two central atoms in here. I'm going to focus on one of them first, and then we're going to work our way through this. Remember, we want to count how many electron groups are there. So let's focus on this particular carbon right here. Carbon here is bonded to three things: this hydrogen, and the other carbon. So that's 3 electron groups. Okay, because it has 3 electron groups, this geometry is trigonal planar. And because there's no lone pairs, the shape is also trigonal planar. So this thing is flat. And if we look at it, you might already be seeing this, but I want to point it out just so we all see it. The other half of this looks exactly the same, but we can figure it out this way too, right? If we look at this carbon, right, it's also bonded to 3 things: a hydrogen, and the other carbon. Okay, so again, it's 3 electron groups. And because we have 3 electron groups and there's no lone pairs, both the geometry and the shape are trigonal planar. Okay, that doesn't look like what I wanted to spell. Trigonal, there we go. Yeah, so once we know that, we can kind of get an idea of what the molecule as a whole looks like. Okay, because really this half of it is trigonal planar, and the other half of it is trigonal planar. And the only way this is going to work for us is if all 6 of these atoms are in the same plane. And so this dude is flat, okay, and looking like that. And that's going to have a lot to do with how the chemistry of this thing works, which we'll get into when we get into organic chemistry as we do that. Okay, and we're gonna see how this goes. All right. While I'm thinking about it, I want to say our secret word for this is Starscream. Um, And then, yeah, let's, excuse me, let's look at another example. This is glycine. Glycine's an amino acid. This is also going to show us how we can kind of piece together a Lewis structure that's written for some weird organic crap that um, in this kind of condensed nomenclature here. Okay. Remembering that hydrogens can't be the central atom. So really our core here is, I don't want red. Our core here is nitrogens and carbons. So we have nitrogen that's stuck on a carbon, and the carbon on the end has 2 oxygens bound to it. Okay, there's our core based off of, we have NH2, CH2, CO2, and we have H at the end. Okay, NH2, so we have 2 hydrogens on this nitrogen dude here. Okay, this carbon also has 2 hydrogens, right? CH2, so there's CH2. Then we have CO2, that one's done. And then we have H on the end, so I just stick H on the end. Right, this hydrogen is bound to one of these oxygens. Okay, and it doesn't really matter which one you do. I just did it this way because it looks nice. Okay, then we're just giving everybody enough valence electrons to have 8, which means this oxygen gets 2 lone pairs, this guy gets double bonded, and 2 lone pairs. Nothing happens on the carbon. This nitrogen is short too, so we'll give it a lone pair. All right, this is what glycine looks like. And if we look at it, right, hopefully we notice there's 4 central atoms. We have a nitrogen, we have a carbon, we've got another carbon, and we have an oxygen. Okay, and we can figure out kind of a vague idea of what glycine looks like if we can do VSEPR theory on every one of these central atoms. Okay, so let's look over here. We'll start at nitrogen and work our way across. So our nitrogen has 4 electron groups, right? 3 bonds and a lone pair. Yeah, groups. So this means our geometry is tetrahedral because there's 4 things, but it means our shape is trigonal pyramidal, or pyramidal if you want, um, because there's that lone pair on the top. Okay, we go 1 over. Let's look at this carbon, right? This carbon here has 4 things attached, right? The 2 hydrogens. That's not a double bond. That's just me making it yellow, right? Hydrogen. We have a carbon on this side and a nitrogen on that side. So with 4 electron groups, I'm going to run out of space if I'm not careful. 4 electron groups. This guy is tetrahedral because it doesn't have any lone pairs. So tetrahedral. Okay. If we look at that carbon that's next over, the one with the double bonded oxygen, this carbon here, okay, if we're counting electron groups, then this is 1 over here, this is 1 over here, and this is 1 going up here. This is 3 electron groups. I'm making my picture look awful, so if you're stuck on this, I'm sorry. I have another picture after this too that'll help a little bit. Um, again, there's no lone pair, so the geometry and the shape are going to be the same thing. Because it's 3 electron groups, this is trigonal planar. Okay. Lastly, we have the oxygen on the end. This guy here. All right, notice right away there's 2 lone pairs. 1, 2. It's bonded to the hydrogen on one side and the carbon on the other side. So this is 4 electron groups and 2 lone pairs. So 4 electron groups makes it tetrahedral. And 2 lone pairs means this guy is bent. All right, so you can already kind of see, like, if we're looking at bigger things, it's going to be more difficult to determine if, to kind of see in our head what the overall molecular shape of this big ass thing is going to look like. Okay. That's why a lot of us are going to work with models. So here's a model. This is what glycine kind of looks like in a ball and stick model. And you can see we've kind of predicted everything the way we wanted it to be. Trigonal pyramidal on the nitrogen, 1 carbon is tetrahedral, 1 is trigonal planar, and the oxygen on the end is bent. Okay. Um, so really the key here is, can you figure out what a central atom geometry and shape are and know all the names and be able to spell them? Okay. I hope that kind of helps. Let me know if you need anything. And I'm here for you, and I'll see you in the next one.